Okay, let me give you a moment to copy this example down.
Professor, quick question.
Yes,
Is
yes.
is there a way to use Laplace transform if we are that's to solve a differential equation which doesn't start at y of 0, let's say at y of 1 or something? Do we need to do a substitution or something?
It's a good point because those Laplace transforms of derivatives, they have like y of 0 in them and y prime of 0, right? So that, gee, I never even really never thought about that question. I'll make a little note of it, Michael, and maybe I can do a little investigating on that. Okay, sound good?
Okay,
I'm gonna
thank
make.
you.
All right. So initial conditions. Very nice question. All right. Okay, and all right, so let's take a look at this here. We want to find the Laplace transform of a function of t defined by t times the unit step function at t minus 2. Okay, so the unit step function, remember, so the unit step function at t minus 2 okay, so if we look in section 7.3, the unit step function, well, this would equal 0 when t is greater than or equal to 0 and less than 2. And the unit step function will equal 1 when t is greater than or equal to 2. And for this problem, because we have a unit step function in here and we only have a t in front of the unit step function, well, we know the second translation theorem is going to be involved. And we're going to have to do something with this t, this function t in front of here. What do we want? What do we want, class, in front of this unit step function at t minus 2? What function do we want to have in there? We want to have a t minus 2 in front. Okay, that's what we want. So let's go to the solution here. I mean, we want that. We want that, right? So, okay, always keeping the table of Laplace transforms in mind. So here's the second translation theorem. The Laplace transform of a function defined by the function at t minus a times the unit step function at t minus a would equal e to the negative as times the big f of s function, which is, you know, that big f of s function is just the, I mean, this is just the Laplace transform of f of t. So because I want a function of t minus a, well, I mean, I want a function of t, I want a t minus 2, not a t, in front of that unit step function. So I'm going to write t as t minus 2 plus 2. And then what we can do is the t minus 2, I can distribute that. And the 2, I can distribute that also to the unit step function. And that's going to get me then here.
What do you mean by distribute?
Well,
I'm confused.
so I'm taking t minus 2 and multiplying it by the unit step function. That gets me this here. And then I'm taking 2 and I'm distributing it on the unit step function, and that gets me all this. And then the little Laplace transform of the sum is the sum of the Laplace transforms. Antonio, are you all right with that?
Yeah, I'm not following. So I see
You're-
you
you're-
have the 2 multiplied by the u gave you the 2 Laplace u. I get that. So then what's
Let me
this
ask
a
you-
prime?
Let me ask you this. This here is actually a 1. This is a number 1 here.
Oh, okay.
That's, so I think you'd agree that t minus 2 times the unit step function
Mhm.
plus 2 times the unit step function. The unit step function is a common factor, and so you could write
okay.
that like that there. All right, very good, very good.
That makes sense.
All right, well now what we're going to do is this here, this Laplace transform, I'm ready to use the second translation theorem because I have a t minus 2 and I have a unit step function at t minus 2. See, I have a function at t minus a times the unit step function at t minus a. I have a, now the function, what is the function? Well, t minus 2 is like t minus 2 to the first power. So the function is just equal to t. And so the Laplace transform of t to the first power is 1 factorial over s squared, and then e to the negative 2s is in front because a equals 2. Are there any questions on that?
Is that 1 to the first power? And
That is, well, so you mean here, Matthew?
No, I mean one step like directly below that, where it says e to the negative, like right once you've applied the second translation theorem. Like I get the first part, e to the negative 2s.
Oh, here. Oh, okay. You mean that this part here. So in front of the unit step function.
No. I mean below that in the next step, once you have
okay.
applied the second translation theorem.
Yeah. So, well, first of all, I need what functions in front of the unit step function. Okay, the only function could be a 1, right? But I got to write the 1 as t minus 2 as a function of t minus 2. The 1 has to be a function of t minus 2. Oh, okay. Well, I'll write 1 as t minus 2 to the 0th power.
Okay, I'm sorry. Hold on. I meant this.
That's a 1 factorial.
Oh, 1 factorial. Okay.
Yeah. Okay, all right. And so for the second Laplace transform, the 1 I write as t minus 2 to the 0th power. And then now, the Laplace transform is in the right form so that I can apply that second translation theorem. And that's what we do. That's what we do. So the Laplace transform of 1 is just equal to 1 over s, right? And that's how you get the 1 over s here. And then, you know. All right, let me know if you have any questions. All right, are we ready to move to another example? All right. All right, give me a few thumbs up then when you're ready. Okay, all right, very good. Then onward. Okay. Now we're going to do an inverse Laplace transform. So let me ask you, you see the s over s squared plus 9. Okay, so what would be what does that remind you of in terms of Laplace transforms? Okay, good, Antonio. A cosine of 3t. So let me show you how we would do this. Okay, so the s over s squared plus 9 is the big F of s function. K squared equals 9, k equals 3. Now, the Laplace transform by the second translation theorem, we know that this is true, this equation. But that means then that the function of f at t minus a times the unit step function at t minus a would equal the inverse Laplace transform of e to the negative as times f of s. And that's what I'm trying to tie in over here. You know, that's what I'm tying in here. So the Laplace transform of the cosine of 3t equals s over s squared plus 9. Okay, so the f of t minus a, okay, the f of t minus a, well, the little f function is a cosine function, cosine of 3t, I should say, but you're having it at t minus a. That's your variable, so to speak. Well, it's what you're putting in, you know, the function. So hence t minus pi over 2. Because you got the pi over 2 here, that's your a. Times then the unit step function at t minus pi over 2. And there we go. Are there any questions?
Wait, are those parentheses, or were you trying to erase them, or?
They are parentheses. They just didn't come out on the, hold on, let me make them a little nicer here. There we go. All right, Matthew? Everybody, is that good? The scanner didn't pick up those parentheses well. Let me make them a little darker on my notes. Excellent, very good. Getting a lot of good questions here. I think people are, you know, they're want to do well in differential equations. That's great. Excellent. Excellent. Are there any other good questions? Okay, well now let's actually solve a differential equation. Let's solve a differential equation. And I'm going to solve a first order differential equation. But of course, we can use the operational properties to also help us solve second order differential equations and you know that like and even third order differential equations. But let's just look at a nice example here. So, okay. How many see this example and they say, oh man? How many are thinking, oh my goodness, I got a piecewise function on the right-hand side? How many kind of don't like those problems when the function on the right-hand side is a piecewise function? Okay, Matthew doesn't like those. Who else? There must be a few of you who maybe don't like isn't the right word. Okay, Andrea is not a fan. But the thing is, with Laplace transforms will help us tremendously when the right-hand side is a piecewise function. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Now, what I'm going to do is I'm going to try to get through this example. I want to try to get through the example as far as I can, but again, I may have to. I mean, it might be. Well, let's just see what we can do. I may have to kind of, in the end, just kind of close out and have it on the recording, and maybe you could, then later put it in your notes. But let's just see what we can do. I really like to do things with you in person, because then you ask good questions. So this right-hand side, okay, we can write that function in terms of a unit step function. Okay, in terms of a unit step function. That's right, Michael, exactly right. So let me show you what that would be. I'll go to the next page here. Okay. So the differential equation can be expressed as y prime plus y equals 3 times the cosine of t times the unit step function at t minus pi. Now that works because that unit step function will equal 0 when t is greater than or equal to 0 and less than pi, and the unit step function will equal 1 when t is greater than or equal to pi. And that's exactly what the right function is, what that f of t function is. Are there any questions?
So does the piecewise function have to have like the perfect conditions for this to work, or like? I noticed
I'm sorry, the first perfect conditions, Antonio?
Like the starting conditions are 0 is less than t is less than pi, which is the same as the u, right?
It is convenient, isn't it, when it's that way? Let me just see here in the book real quick to see if they you can always manipulate functions, but let's see here. Like in the book, for instance, if you look at example 6, they write a function. Well, actually, if you look at figures 7, like figure 7.3.4 in the textbook, they show a function that is somewhat different than unit step function. It's a combination of unit step functions. So you can construct different looking functions based on unit step functions. But in this problem, we're just keeping things pretty simple. But yeah, maybe next week we can talk about that a little bit. That's a good question. For now and for your homework, it should be normally pretty simple.
Wait, where do we get this unit step function here?
Well, I know that 3 times the cosine of t times this unit step function, I know that will equal, I know that that's going to equal 0. So here's what I'm trying to say. Here's what I'm trying to say here. This here on the right-hand side will equal 0 when t is greater than 0 and less than pi. because the unit step function equals 0 when t is between 0 and pi. And it'll equal 3 times the cosine of t when t is greater than or equal to pi. Because the unit step function equals 1 when t is greater than or equal to pi. So writing that piecewise function on the right side, I can express it as this function here. And that's nice because now I can take the Laplace transform of both sides. And, you know, this on the left side, the Laplace transform of y prime is just, which is, you know, I mean, the Laplace transform of y, we can denote that as big Y of S. I use the capital Y because, you know, I have a little y. Little y is my function, so I'll let big Y be my Laplace transform. Just like if I had a little function f, the Laplace transform would be a big function f. So, you know, the Laplace transform of y prime is just S times big Y of S minus Y of 0. And the Laplace transform of y is just big Y of S. And then on the right-hand side, because I have a unit step function t minus pi, I got to rewrite the cosine of t on the right-hand side. So the cosine of t can be written as negative cosine of 1 times t minus pi. That will equal the cosine of t. And that's nice because then I can apply the second translation theorem to get this, this Laplace transform on the right-hand side. Zachary, oh, okay, Zachary will, okay, so now in the partial fractions, Zachary had a question. Where did the negative 3 times e to the negative power over s go? Well, what I'm going to do in the partial fractions is I'm going to take the s divided by s plus 1 over s squared plus 1 and rewrite that in terms of partial fractions. And then whatever partial fraction expansion I get, I'll multiply through them by e to the negative pi over s when I'm done. It's legal. It's certainly legal to do that.
Professor, where did you get how did you get -1 for the Laplace transform of that's where
You
did you
mean
get the
like
negative?
up here?
Yes.
Well, I said to myself, how can I write the cosine of t? If I want to write the cosine of t as a cosine of t minus pi, then I have to put a negative in front of it so that the two functions are equal. It's like you have to graph, you know, if you graph the cosine of t and you graph the cosine of t minus pi, oh, okay, well, you'll see that they're like opposite. Okay, well then put a negative in front of the, you know, that.
Okay. I see it.
So you have
Thank
to
you.
do a little experimenting, but it's usually not more complicated than that. Good question. And this is a reason why I like to go over this in the class, you know.
What is this sy of s thing? I'm still like.
Which one, Matthew? Where? Maybe draw for me where you're at. Oh, up here. Yeah. So the Laplace it's like the Laplace transform of f of t is denoted as big F of s, right?
Oh,
so
and you're saying that's
it's notation. It's notation.
y of s is the capital Y of s is equal to f of s, capital F of s?
It's just instead of using capital F, I'm using capital Y. It's just
Okay.
more appropriate notation.
And then is that a capital S next to that capital Y and a lowercase y?
This is
in the next
they're all lowercase s's.
Oh, all lowercase. Okay. And
They're
then, but
all
it's a
lowercase.
lowercase y in the second term, but not the first
That's
term.
right. Here, this is a lowercase y. That's right. And the initial condition was y of 0 equals 5. Yep, that's right.
And Professor, just to ask, we could also use that's rather than using this second translation theorem, we could also integrate that piecewise function like we did in the first lectures of the Laplace transform, right? Like we integrate from 0 to pi and then integrate from pi
You
to infinity.
could. You got to be careful here. You could use the definition, but it's probably
Yes.
more work to use the definition to take the Laplace transform than to just kind of figure
Yeah,
out
it's
what.
going to really be more work.
On the final exam, I'm going to want you to do it this way. I want you to demonstrate that you know the rules.
Okay.
For like the second translation theorem and stuff. That's important. You're going to find it to be better to do, Michael, that way.
Okay.
All right, very good, very good. And the partial fraction expansion. I really did it two ways here, just so you could see it. I really did it two ways. Two different ways.
This step right here, this is a 5 over.
That's a
S plus
5.
1? Okay.
This is a 5. Yep. That's a 5. So I divided through by s plus 1. That's right. Now again, class, we're probably going to come up a little short on time. I do want to let you see your MATLAB grades, so we might come up a little bit short on time in terms of discussing this example. But I'll make sure that the full solution is seen in the recording, and we're gonna go right up to as far as we can, and I think you'll be fine. So now we know what A, B, and C are. A is equal to -1/2, B equals 1/2, and C equals 1/2. And when you're ready, I'll go to the next page. I know you're probably still need a few moments, but when you're ready, give me a thumbs up and I'll go right to the next page. Okay, very good, Antonio.
On the next page, you write out the full, like, since we've gotten the values for the partial fractions, you write out the full, like.
That's right,
text.
and
Okay.
that's right. And here I am on the next page, where I do write out everything. Let's see here now. One moment. Yes. So let me just see here now. One moment. Okay, so the negative 1/2 is the A. Okay. And then B is 1/2. And C is 1/2. Okay, so I was trying to help you on the copying. Okay. But yes, the partial fraction expansion is there. This is a 1 here. This is a 1. So really now you're just applying the rules. You're applying the rules. And there's a lot of second translation theorem going on here. We need the unit step function in our solution we're going to need it in our solution. And what are we doing here? We're finding the solution. There it is, y of t. We take the inverse Laplace transform. Okay. And of our equation, and we get y of t. That's our, and the solution, of course, is going to be a function of unit step functions, because we have a piecewise function in our differential equation on the right-hand side. So this is going to take a little time for you to look at and be comfortable with, but the details are there, and you'll see some problems like this in the homework that's due next Tuesday. The homework that's due Sunday will be just finding, you won't be solving differential equations. You'll be just doing inverse Laplace and inverse Laplace transforms and applying the rules and so forth. But then Tuesday's homework, you will have some then solving differential equations problems using Laplace transforms. Now I'll mention one thing here. I know let me just show you the last page, and then I know you're copying, but let me just show you the last page here. So it's in the recording. What I do is I have these unit step functions. Okay, in other words, y of t, the solution to this differential equation is in terms of all these unit step functions. Well, I know when the unit step function equals 0, and I know when it equals 1. So you could apply that. Hold on here, I'm on the wrong way. What is this? Hold on. One moment here. Oh wow, this is you know what, I had the pages backwards. All right, what I'm going to do, class, well, Well, no, it's okay. It's okay. I didn't have the pages backward. This was an extra page. This here, you can write. So let me go back here. Let me go back. What I'm trying to say is I left out one page. I left out one page of work because I was worried we wouldn't finish, you know, and we are even 1 minute over time. But what I can do is I can make a separate. How many feel another recording of this example, this last example, might be helpful? How many would kind of appreciate another recording? Okay, Paige would. All right, we've talked about it, and what I'm going to do is I'm going to do a separate. Andrea would. Okay, I'm going to do a recording then before the weekend. I'll make a new recording and of this example, and I'll add it then under course content where the recordings are. It'll be there. Okay, but I'm very happy at least we were able to go over a good portion of this example. And so, okay, you're welcome, Christopher. Hey, class, if you go to your Blackboard, go to Blackboard, MATLAB grades for number 5, 6, and 7 are visible. They are visible if you go to the Blackboard. Let me stop the